Hello everyone, my name is Raina Dijut and welcome to my LeetCode problem solving video. In this video I'm going through 5 LeetCode problems and not just explaining what the solution is, but how I got to the solution and what my intuition was when I first encountered the problem. So without further ado, let's get into the first one, which is function composition. So this problem looks simple at first, but it actually has a subtle catch that tripped me up when I was trying to solve it. So the problem is that given an array of functions, return a new single function that changes them all together. The keyword is from right to left. So you run the last function first, take its output, pass it on to the second to last function, and so on and so on. So my first attempt at this was just a regular loop, call each function on X in order, but that goes left to right, which is backwards from what this problem is asking us to do. Then I thought about reversing the array. That works, but while I was researching this, I found a JavaScript method that I hadn't used before, which is called reduce right. So as we can see, the reduce right is right here, and basically it's just like reduce. So it walks through an array and accumulates a result, but it starts from the end and moves towards the beginning. That's exactly what function composition needs. So the solution is handle the empty case first by returning an identity function. That's just this x is equal to or greater than x, which returns whatever you give it unchanged. Then for a non-empty array, return a function that uses reduce right. The accumulator starts at x and each step calls the current function with the running result. So walking through the code, step 1 is empty array equals the identity function. And then step 2 is start from the rightmost function, which is the reduce right, and then ACC starts at x and then becomes the result of each function call. So reduce right iterates from right to left, ACC is the running result, which starts as x, and then this function ACC calls the current function with whatever the previous result was. So the next problem is this memoization. This one is really interesting to me because it's a concept that shows up everywhere in programming once you start looking for it. So the idea here looks very complicated, but is actually very simple. If you've already computed something, don't compute it again. Just remember the answer. The problem gives you a function and asks you to return a smarter version of it that has this memory built in. When I first thought about it, I imagined a notepad. So every time someone asks me a math question, I write down the question and the answer. Next time they ask me the same question, I don't have to do the math again. I just look at my notepad and tell them the answer. So in the code, that notepad is this map. Every time the wrapped function gets called, I build a key from the arguments. I just join them with a comma to get a unique string like 2, 3. Then I check if that key is in the map. If it is, then I return the cached result. If it isn't, I call the real function, store the results, and then return it. The args ... spread syntax is important here. So it lets the wrapper handle functions with one argument like fib or 2 arguments like sum without needing separate versions. So one thing that the problem specifically calls out, which is the 2 and the 3, and 3 and 2 are different keys. So my join, comma, approach handles that automatically. Those produce 2, 3 and 3, 2, which are 2 different strings. So walking through the code, the first step is we create a map to store cached results. Then we return a new function using this ... args to capture any number of arguments. We build a cache by joining args with a comma, so the args.join with that comma here. Then we check if the key is already in that map. If yes, then we return the cache value. If not, then we call the real function with the original arguments. Then we store the results in the map under that key, and then we return the result. This concept clicked for me when I thought about it like a dictionary. So every time the function gets called, I check, have I seen these exact inputs before? If yes, then I return what I stored. And if no, then I run the real function, and then I store the result, and then I return it. The hard part is the key. So how do you turn an argument list like 2, 3 into something you can look up in a map? My first thought was to use the arguments directly, but objects and arrays don't work as map keys by reference comparison. The cleanest solution for these specific inputs, all integers, is to join the arguments into a string with this args join comma. So it's 2, 3. The next problem is this debounce, and this one took me the longest to fully understand because the concept is a little counterintuitive at first. So here's the idea. We have a function that might get called a lot in rapid succession, like a search bar firing on every keystroke. You don't want to run the function every single time. You just want to wait until the person pauses, wait until there's been a gap of however many milliseconds, and then run it just once with the most recent input. The real world version I kept coming back to is if somebody is typing in a search box, you don't want to hit the API 20 times as they type hello. You want to wait until they stop for, let's say, 300 milliseconds, then fire one request. So my first attempt at this was just set timeout. Delay the call by t milliseconds. That handles the delay part, but if you call the function 3 times in a row, you get 3 delay calls. That's not debouncing, that's just really slow functioning. So the fix is this clear timeout. Before scheduling a new timer, cancel the previous one. So every call wipes out whatever was pending and then starts fresh. Only the last call in any burst actually survives long enough to execute. The key insight I had to figure out, which is this timer has to live outside the returned function. If it were inside, it would reset to null on every call, and clear timeout would never have anything to clear. It would have to persist between calls. Clear timeout null on the first call is safe. JavaScript just ignores it, so no special case needed for the first invocation. So if we break down the code, the first thing we do is we declare a timer variable outside of the return function. This persists between calls. Then we return a new function that captures this ... args. Every time it's called, we first clear timeout timer, so we cancel any pending execution. Then we set timeout, so we schedule a new execution t milliseconds from now. Store that new timer ID in timer so the next call can cancel it. So this next problem, allow one function call, this is the most straightforward of the 5 problems, I think, because it teaches something really important, which is closures. So the problem says, given a function, make a version of it that can only be called once. First call executes normally, every call after that returns undefined. The solution is a Boolean flag. So it started as false. When the function is called and the flag is false, run the real function, flip the flag to true, and return the result. Any call after that sees the flag is true and then just returns undefined. So the thing I had to understand, and this is the same pattern as the Debounce problem, is that the called variable has to live in the outer function scope, not in the returned function. If it were inside, it would reset to false on every call and the flag would never stick. This is what is called a closure. The return function closes over the called variable from its parent scope and keeps a reference to it. So every time the return function runs, it's looking at the same called variable. I also store the results separately, which matters if fn returns something falsy like 0 or false. If I tried to get clever and just check if result, I'd have a bug for those cases. Storing it in its own variable and returning it explicitly is the clean approach. So going through the code step by step, step 1 is declare a called Boolean flag initially false. Then we return a new function with ... args. On each call, we check if called is false. If it is, then we set called to true. We run the function, and then we return the result. If called is already true, then we return undefined, and then we don't run the function. So our final problem is this climbing stairs. So I learned that it's probably the most famous beginner dynamic programming problem, and I had to spend a lot of time researching what the heck this problem is even asking. I didn't see the pattern naturally on my own, but once it clicked, it was one of those like, oh, of course it is kind of moments. So the problem is that we have a staircase with n amount of steps. You can climb 1 or 2 steps at a time. How many different ways can you get to the top? When I first read this, I tried to think about combinations. So for n equals 4, I started listing paths manually. So 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 2 plus 1 plus 1, and 2 plus 2. So that's 5. Then I noticed a pattern that n equals 1 is 1 way, n equals 2 is 2 ways, n equals 3 is 3 ways, n equals 4, 5 ways, n equals 5, 8 ways. That's 1, 2, 3, 5, and 8, which is called a Fibonacci sequence. So a Fibonacci sequence is basically a sequence of numbers where each number is the sum of the 2 before it. So it starts like 0, 1, and then from there it's 0 plus 1 equals 1, 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 3 equals 5, and so on and so on. So in coding terms, it's a classic example of a problem that can be solved recursively because each result depends on the previous result. or iteratively, which is usually more efficient. The reason it shows up in so many LeetCode problems isn't because the sequence itself is important, but because it teaches a pattern, breaking down a problem into smaller subproblems. That's the foundations of things like dynamic programming, where instead of recomputing the same values over and over, we store them and then we reuse them. So anytime that I see a problem where the current result depends on the previous two results, that's usually a hint that it follows a Fibonacci-like pattern. So if we break down the code step by step, the first thing that we're doing is handling base cases. So if n is less than or equal to 2, then we return n. Basically, if n equals 1, return 1. If n equals 2, return 2. Then we initialize two variables. So this prev2 equals 1 is the amount of ways we can reach step 1. And then this prev1 equals 2 is the amount of ways we can reach step 2. Then we loop using a for loop from step 3 to step n. Then we let each iteration, which is this line right here, then we slide the window. So prev2 equals prev1 and prev1 equals current. That's just us sliding the window. So we're looking at 1 and 2 in a window, and then we slide the window and we're looking at 2 and whatever that next number is. Then after the loop, this prev1 is what holds the answer. So those are all of my LeetCode problems for Module 8. These problems have consistently gotten harder, and so I'm scared for next week. I'm scared for the next 8 weeks, but I hope this made sense. Thank you for watching, and I will see you on the next one.